Alright, this time we're moving into the math part. But don't worry, it's much simpler than it looks. Let's go. Before diving deeper, let's review what queries, keys, and values actually do in the attention mechanism. Remember, attention means defining my new, deeper identity inside a group. It's like being in a classroom. You redefine who you are by how you relate to your classmates. Now imagine a student asking, "What's me?" to the classmates in their own class, which is Classroom A. That's what self-attention does. It helps each member learn from others within the same group. But sometimes you may ask, "What's me?" to the people in another class, which is Classroom B. That's cross-attention. It happens between different groups where one learns from another. Now, let's switch back to language. We have the sentence, "I love to code." Each word, or token, will become an element in a group, ready to exchange information through attention. For the word I, we ask, "What's I?" in the sentence, "I love to code." Self-attention helps the word I look at every other word, including itself, to redefine itself in context. Then for love, we ask the same question, "What's love?" in "I love to code." Now, love learns its meaning by connecting to all the others. Next, the word to looks around as well, asking, "What's to?" among the other tokens. Finally, guess what? Code does the same thing. It finds out what it means within the sentence. Through the interactions with I, love, to, and code, it gains its contextual identity. And that's how the attention mechanism redefines every word through shared understanding. Now let's extend our example. We have the same idea, but now we add a new French language, j'adore coder. Each sentence, English or French, has its own tokens that will later connect through attention. Here, the English token asks, "What's I?" In the French sentence, this is cross-attention, where tokens from one sentence attend to another sentence to connect corresponding meaning. The important thing to note is that every token, no matter which sentence it's in, gets its own query, key, and value in both self-attention and cross-attention. These are the essential ingredients for calculating attention. Here you can see that each word, I, love, to, and code, has its own Q, K, and V. They're the internal representations that let each token ask, offer, and share information during attention. Now that we know every token has its Q, K, and V, let's represent them as actual vectors, the form neural networks can process. Remember, neural networks only work with numbers. That's why we turn each word into vectors. From there, the network computes Q, K, and V vectors through linear transformations, all ready for attention calculations. Each colored block here represents the Q, K, and V vectors for each token. These vectors together determine how attention weights are computed between words, forming the basis for contextual understanding. Finally, as we have seen before, they all come together. The query interacts with keys to compute weights for linear combinations, showing how relevant each word is to another. Those scores are then used to weigh the values, producing the final contextual representations. This entire process is elegantly captured by the equation you may be familiar with. Now, we'll explore how math, specifically linear algebra, makes calculating attention efficient. Don't worry if math sounds scary, we'll take it one step at a time. The dot product is a simple operation that measures how two vectors relate to each other. If two vectors point in a similar direction, their dot product is large, meaning they're closely related. That's why attention uses dot products, to see how much one token should care about another. Let's apply this to language. We want to know how relevant the token love is to in the sentence "I love to code." Since both words are represented as vectors, we simply compute their dot product to measure this relevancy. Even though token embeddings are vectors, in attention, we don't just use them directly. Instead, we use the query vector of one token and the key vector of another. The dot product between a query vector and a key vector gives us the measure of relevance. for how much the word love attends to the word to. But we don't just need one dot product. We need every token to compare with every other token. That's a lot of dot products. To handle this efficiently, we use matrix multiplication, which computes all those dot products at once. So instead of one-by-one calculations, we batch them together. That's the power of linear algebra. Let's do a quick count. If our sentence has 4 tokens, I, love, to, and code, then each query interacts with 4 keys. That means 4 times 4 equals 16 dot products in total to compute relevancy. Imagine if the sentence becomes longer. We'll have even more dot products to calculate. Fortunately, we can handle all of them efficiently using matrix multiplication. All those dot products are stored in a single matrix, Q times K transpose. Each element in this matrix represents one dot product between a query vector and a key vector. This matrix not only tells us how every token relates to every other token, but also does so efficiently and compactly using matrix multiplication, which captures all those relationships in one elegant operation. Each dot product value can range from -infinity to +infinity, which could make attention unstable. So we normalize these values, adjusting them so they're balanced and easier to interpret. Moreover, we make them sum up to 1 so they can act as scaling factors when combining the values. First, how to normalize. To improve stability, we divide each weight by the square root of dk, the dimension of the key vector. And then, we apply a softmax function, which ensures all weights are positive and sum to 1. This creates smooth, normalized weights that the model can use effectively. These normalized weights are called attention scores. So, this softmax equation gives us the final weights used to blend the value vectors to complete the attention process. All the pieces come together. We get the attention score matrix, the result of softmax equation. Each cell here shows how strongly one token attends to another. This matrix captures all pairwise relationships between tokens, doing so efficiently and compactly through matrix multiplication. It's not just fast, it gives us the full attention landscape in one elegant structure. Next, let's look at the value vectors V. We're almost there. Each token, I, love, to, and code, has its own value vector. We stack all these value vectors vertically to form a matrix V. These values contain the information that will be passed forward once attention decides how important each token is. We then multiply the attention score matrix by the value matrix V. This operation combines all the value vectors, scaled by how much attention each token gives to others. So, the output for each token is a weighted combination of all the values. The beautiful part is that matrix multiplication not only determines relevance, it performs all these combinations efficiently and compactly in one step. Now we can see how it all fits together inside a self-attention block. From the token embeddings, we create queries, keys, and values using their own projection layers. These pass through the attention formula to produce the updated representations. This whole process, powered by linear algebra, lets each token understand the context of every other token, efficiently and beautifully. And there we have it, the full picture of how self-attention works step by step. In the next session, we'll look at what comes after the attention block and extend this concept into multi-head attention, where multiple perspectives of attention work together to capture richer relationships. We're almost ready to see how the entire transformer architecture takes shape. See you later.